Well, good morning. This is a trial run. So we're going to see if this video thing works, even though we'll see what happens, okay? So the first thing I'd ask you to do here is to graph each of these functions on the same axis. So we know from our parent functions, we also know from our calculators, we can type all of these in, or we can just think it through. So I'm going to try to talk my way through this here, because you know, I love to talk my way through. So the first parent function we have, or the first function we have, I'm going to graph in this brick color, and it's y equals the square root of x. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, 1, 2, 3, 4, 2, the square root of 9, 5, 6, 7, 8, 9 is 3. So my graph looks a little something like this. So when I connect the dots, let's see if I can do a fairly decent job. Not too shabby. So what's going to happen here now is I have that graph, so now I'm going to pick a different color, and it says to graph the square root of x plus 5. Well, the first thing I'm worried about is, hey, I can't take the square root of negative numbers, so I'm going to try to start with negative 5. What is the square root of negative 5 plus 5? Well, negative 5 plus 5 is 0. So 1, 2, 3, 4, 5, and 0. So what happens if I put in negative 4? Well, negative 4 plus 5 is 1, and the square root of that is 1. If I put in negative 3, I get a decimal. If I put in negative 2, I get a decimal. If I put in negative 1, the square root of negative 1 plus 5, negative 1 plus 5 is 4, the square root of that is 2. If I put in 0, I get a decimal. If I put in positive 4, 1, 2, 3, 4, I get 3. So my graph is going to look a little something like this. Hopefully yours is a little better grid. But if it were physically possible for you to pick this up and move it over, they should be pretty close to each other. So basically all we did was slide our graph 5 to the left. So the last one it's asking us to graph is, I'm going to do brown, and it's asking us to graph that the square root of x plus 5. Well, the square root of 0, we can do that, is 0. 0 plus 5, 1, 2, 3, 4, 5. Then it asks us to graph 1. The square root of 1 is 1, plus 5 is 6. The square root of 4 is 2. 2 plus 5 is 7. So again, my graph is looking a little something. It's like this. Because I was off the chart, it probably won't match up as pretty. But you can see they're pretty close. And basically what we've done is we've just done a translation. So what happens to our graph when we look at this? Well, you probably type this in your calculator, at least I would have, but hey, that's me. You do you, I'll do me. So we've got 1 divided by x, which I know has an asymptote at x equals 0 and y equals 0. And I also know that it has the ordered pair 1, 1 and negative 1, negative 1. And if I put in 4, I've got a fourth. If I put in a fourth, I've got 4. So it's going to look a little something like this. It's going to be kind of close to my, oh, that's a terrible graph. Let me try again. Maybe if I come in from the side. Da, 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 da. A little bit better, but not perfect, but you get the gist. Wow, that is a big old arrow. Likewise again here. So we had our asymptotes there at 0 and 0 for our pink graph. Our second equation is y equals 1 divided by x plus 3. I'm going to graph that one in blue. And the only change here is instead of my asymptote, vertical asymptote being at 0, it's now at negative 3. So instead of negative 3, instead of 0 being my asymptote, I've got negative 3 being the asymptote. So it's going to look a little similar some people, I probably should draw my asymptote here. And get an asymptote drawer. And let's go with, we're doing blue, right? We're doing blue. So let's get our asymptote. There's my asymptote. Right? Okay. And now I'm going to go back and I'm going to sketch this graph. It's going to get close to the x-axis again. And it's going to get close to x equals -3. It's not very pretty. Whoa! That one went over. Can't do that. Can't cross that x-axis. So there's my second graph. And again, if it were possible, it's not as easy on this graph, but if it were possible to move these, well, look at that. They should be pretty darn close to each other as far as our grids. Then the last one I think I'll do in purple. So graphing the last one in purple, this says 1 over x plus 3. So I still have the same asymptote of 0, but vertically I've moved everything up 3. So instead of having a horizontal asymptote of 0, I now have a horizontal asymptote of 3. So 1, 2, 3. So there's my horizontal asymptote. And then I'm just going to sketch in my grid in my graph. I might have actually got something pretty decent there. That one looks pretty. I mean, it ain't sexy or nothing, but it'll do. Okay. Ta-da! And again, if I took this down, it's right on top of that pink one. Okay, so you can see what the grids are actually happening here. What we're going to do is we're going to look at parent functions today. This happens to be a picture of my sister, my dad, and myself. And we're going to look at parent functions. You'll notice that we do kind of look alike. We all have the same nose, if I stop and look at it. And I really do look more like my dad, and my sister looks more like my mom, but we don't have a picture of all four of us here. You can also see these right here. These hands are all similar. You've got the baby hand, the mama hand, the daddy hand. However you want to do it, or baby, sister, baby, middle kid, oldest kid, however you want to think of it. And we're going to look at how those functions, parent functions, can be altered to make them look like other things. Okay? So what we're going to start by first doing is looking at this function. This is a linear function. It's the graph of a line. We have y equals mx plus b. We have a quadratic function. Has a vertex. Domain is all reals. Range is y greater than or equal to 0. Or whatever that vertex could be. It could be a min or a max. We have a cubic function. Our cubic function is domains all reals. Range is all reals. And we have a square root function. And you can see it starts at 0, 0. Then we have our inverse variation functions, which we just did on the drill. We have the inverse square function, where it's a hyperbola in first and second quadrants. We have the absolute value function. That blue dot shouldn't be there. And we have the exponential growth function. The blue dot is gone. So what we're going to do is we're going to take a second and we're going to fill out our card stock. Filling out our card stock. So I'm just going to do this a column at a time, and it's going to give you some traits for the parent functions, and that will apply not only just to the parent functions but also to their offspring. So this is a linear function. The generic equation is y equals x. Our domain's all reals. Our range is all reals. There are no asymptotes. symmetries, there are none, even though in this particular case it appears to be odd. Because in this case you could rotate it 180 degrees and it would be back on itself. But not all linear functions have that. Does it have a maximum or min? No. The y-intercept is always at b, 0b. In this case it's 0, because it intersects with the origin. And it always has, one x-intercept. Our quadratic function, y equals x squared. Domain is all reals. The range is y is greater than or equal to, this is the y-coordinate of the vertex. Okay, so our vertex for the quadratic equation is negative b divided by a, divided by 2a. And you plug that value in, and that gives you the y value of the vertex. There are no asymptotes. It's always symmetric to the vertex. Your maximum and minimum is your vertex. It's either a maximum or a minimum. Your y-intercept, there is one y-intercept, and it is always the c value. So in this case it's 0 because there's nothing there. And the x-intercepts are 0, 1, and 2. There could be 0 x-intercepts, there could be 1 x-intercept, or there could be 2 x-intercepts, depending on how it opens. Our cubic functions, this one happens to be symmetric to the origin, although not all cubic functions are. General equation is y equals x cubed. Our domain's all reals. Our range is all reals. For a second I thought I wasn't recording. There are no asymptotes, vertical or horizontal. It's symmetric to the origin. There is no max or min, although there could be a relative max or min. The y-intercept is 0, d. And our memory strategy, we don't have one. There is at least one x-intercept. There could be 2 x-intercepts, there could be 3 x-intercepts, but there's at least one. Okay? Our square root function, we have x is the square root, or y equals the square root of x. The domain is non-negative reals. The range is non-negative reals. Our asymptotes, there are no asymptotes, there are no vertical asymptotes or horizontal asymptotes. There is a minimum because this graph does start at the origin and opens up, so we do have a minimum of 0, 0. Our y-intercept is 0, 0. Our x-intercept is 0, 0. And that changes as the graph moves left and right, which we're going to be doing next class. Okay, coming back over to the other side, this is our exponential growth. Our domain's all reals. Now, the equation they've given us here is ab to the x. Sometimes, when you look at this, sometimes the equation that they choose would be y equals b times g to the x. Either of those works. B times g to the x sometimes makes more sense because b is your beginning amount and g is your growth rate, but the exponent is the variable. Okay, so it's b times g to the x. It's all real numbers. Our range is greater than 0 because there's nothing you can plug in for x that would give y to be 0 when it's a power, because anything to the 0 exponent is 1, so that would just be 1 times b. We do have a horizontal asymptote because it can't be 0, so we have a horizontal asymptote. There's no vertical asymptote. It's not symmetric to anything. There is no minimum because it is an asymptote situation. There's no maximum because it goes on forever. It does have a y-intercept at 0a, or if you're using the b times g to the x at 0b. And there is no x-intercept because it can never be, y can never be 0. Absolute value, a more popular function. So we look at this, y equals the absolute value of x. We have all real numbers. Our range is greater than or equal to 0. Since it's greater than or equal to 0, that means we don't have asymptotes. Our symmetry goes through the vertex, much like it does for a parabola. So if you can write the equation for absolute value in vertex form, like you did in Algebra 2, you'll be great. The maximum or minimum is the vertex because the absolute value could open up or down. And in this case, our x-intercept and y-intercepts are 0, 0. Then the last two are the ones that we did on the drill. For whatever reason, the equation editor on Active Inspire does not like to make that fraction bar visible, so I just drew it in. So what we've got here is a situation where the domain is all reals except 0, and the range is all reals except 0. So we have two asymptotes here, a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. It's symmetric to the origin, because if you were physically able to spin this around, you could spin it and 180 degrees and be back on itself. There's no max, there's no min, there's no x-intercepts, no y-intercepts, because those are our asymptotes. And again, the inverse square function, again, it doesn't like to draw that fraction bar. So we know that x can't be 0. We also know that in this case, y has to be greater than 0 because we're squaring x, so there's not going to be negative values. Has the same asymptotes as our previous equation, and it has a symmetry. This one happens to be symmetric to the y-axis, which is the equation x equals 0. There's no maximum or minimum, and again there are no intercepts because the x and y axes are our asymptotes. So, let's talk about symmetry a little bit. Symmetry is something that we don't often talk about, but you can see symmetry in these leaves, with the exception of this hole right here. If we were able to fill that hole in, this leaf would be symmetric. These leaves, the sides are symmetric. And even it looks like the leaf itself, that foursome, is symmetric because it kind of looks like we have a y-axis and an x-axis going through there. But hey, who am I? So let's take a second and just check out this little PowerPoint that's embedded here. My dear sweet friend, the wonderful and talented Mr. Rankin, made this for us. And he did this back years ago, and it's just beautiful. So what we're looking at is symmetry. Symmetry means either reflective symmetry or rotational symmetry. If it's reflective symmetry, that means if you take this side of the graph and plug it in and fold it over onto this side, they would be exactly the same. So when we define symmetry here, we're defining symmetry with respect to the y-axis, and that's what a parabola is. It's symmetric to the y-axis, or wherever the vertex is. So for us, for every point xy on the graph, its reflection over the y-axis is also on the graph. So if we take a look here, we have the ordered pair 1, 1. The opposite of 1 is negative 1. Well, negative 1, 1's on the graph. We have the point 2, 4. If positive 2, 4 is on the graph, if it's symmetric to the y-axis, then negative 2, 4 should be on the graph. That's what we're talking about with this. So we've got 2, 4, we've got negative 2, 4. Now, if we were able to spin this, pace yourselves. If you flip this graph over the y-axis, its own reflection image is on itself. Now that was tight. Mr. Rankin did that back in the day. So check it out again. Just a little invested in that slideshow. Now the other type of symmetry we have is when things are symmetric to the origin, and you can kind of see that right here in this particular flower. So if you look at, there's the center. Hey, look, those appear to be about 120 degrees apart each. And if I were able to rotate this 120 degrees, they would be back on themselves. That's what we're talking about. We talk about symmetries to the origin. So you could be symmetric to the y-axis, or you could be symmetric to a vertical axis. You could be symmetric about a point. For us, we're talking about the origin. This means that every point xy on the graph, then the point negative x, negative y is also on the graph. So here's a beautiful cubic function. So we have the point 4, negative 10. We went right 4, 2, 4, 6, 8, 10. Okay? And then we have this other point over here. So if this is correct, and this is going to be symmetric to the origin, the opposite of 4 is negative 4. The opposite of negative 10 is positive 10. So that works so far. If we actually rotate this 180 degrees, then it's going to be symmetric to the origin. Well, look at that. When we rotated it, it ended up back on itself. And those points are still the same. So when you see Mr. Rankin in the hall, make sure you thank him for this lovely PowerPoint for the symmetries. Okay? Now back to our regularly scheduled program. If it's symmetric to the y-axis, it's something we call even. Now, this we actually talked about in that slideshow that Mr. Rankin made. This definition is for an even function. Symmetric over the y-axis, this is what it needs to be. xy on the graph and negative xy on the graph. If you need to prove it, then you plug in the opposite of x and see if you get the same thing that regular x stands for. That makes it an even function. So to show it algebraically, we're going to check negative x. So we know what f of x is, so we're going to substitute in negative x. So what is f of negative x? So if we're going to show that this function is even, we're now going to do f of negative x. Oh, that's a terrible parenthesis. And we're going to evaluate that, which means we're going to take negative x and we're going to square it. Well, what is negative x squared? It's just x squared. Is this the same as the original? Yes. So since f of negative x equals f of x, it's even. Also means that it's symmetric to the y-axis. If you're asked to show it algebraically, this is what they want you to do. Now, to show that the graph is symmetric to the origin, again, we just showed you this in the PowerPoint. X and y on the graph, then negative x, negative y is also on the graph. That means that our function is odd. Okay, so if we want to show that this function is odd, what do? Well, our definition of odd says f of negative x equals negative f of x. So the first thing we're going to do is we're going to plug in, just like we did before, f of negative x. Anytime you're asked, is the function even or odd, this is your first step. So what we're going to do first is we're going to take negative x, put it in for x, just like we did before. At this time, we're cubing it. So what is negative 1x, or negative x, to the third? Well, negative times negative is positive, times negative is negative. So that's a negative x to the third. So the first question, are these two the same? No. So it's not even. So the second part of this function says that it has to be the opposite of f of x, which means if I put a negative here, what is negative f of x? Well, negative f of x is negative x cubed. Are those two the same? Yeah. So since the opposite of f of x, so we evaluated that, distributed the negative through, which was negative x cubed, is the same as f of negative x. So we plug in the negative x, we get the same thing as the opposite of it. That means it's odd. So if you're asked to do this algebraically, like on a test or a quiz, that's what you need to do. Now there's another type of symmetry, but this isn't for functions. And that symmetry would be if it is symmetric to the x-axis. So if something's symmetric to the x-axis, then it just means that the y's are opposites. So take a pause and decide if each of these functions is even or odd. We already did this one. We already did this one. You decide. Pause the video, answer the questions. So when I look at this, it says f of x equals x. Beautiful. If I put in negative x, does negative x equal f of x? No. Does negative x equal negative x? Yes. So this appears to be odd in the way that it's written just now. How about here? The square root of x. But we can't take the square root of a negative number, so this is neither. How about here? If we put in 1 divided by negative x, that's not the same. But if we did negative f of x, that would be the opposite of this. So that would be odd. It's also symmetric to exactly the origin. Check this out. If we plug in negative x, 1 divided by negative x all squared is 1 over x squared. So this is even. It's also symmetric to the y-axis. Here, it appears to be symmetric to the y-axis. If I plug in negative x, what's the absolute value of negative x? The absolute value of x. Good. So this is also even. Now these are the parent functions as they start out. We can slide them and move them around left and right, and that's going to change things. Is this even or odd or neither? Well, it's not symmetric to anything, so it's a neither. So here it's asking us to prove that this graph is symmetric to the y-axis. When you read the word symmetric to the y-axis, what's that really asking? It's asking you to prove that it's even. So it's asking you to show that f of negative x equals f of x. So you're probably sitting there saying to yourself, oh, Finny, I miss you. I miss you guys too. But you're really saying to yourself, Finny, I see no f of x. But you do remember from your Algebra 2 teacher that f of x is the same as y. So what you really have is f of x equals the square root of 36 minus x squared. So we want to check to see, is this even? So I'm going to get a different color when I do my substitution. So what I'm actually plugging in is negative x. I'm going to do that in red. Negative x. And I've got the square root of 36 minus negative x squared. You're like, you slowed way down when you had to write, Finn. It's true. Alright, so now when I evaluate this, f of negative x, well, what does that equal? Well, does anything happen to the 36? No. So it's still going to stay the square root of 36. So we've got 36 minus, what is negative x all squared? Just x squared. So are these the same? Is the original function and our f of negative x, are they the same? Heck yeah. So there's your algebra that shows they're even. Then it says, determine whether this function is even, odd, or neither. If it appears to be odd, prove it. So one of the things that you could be doing in this case is it could actually be asking you to graph it and see which one it is. But since I have to prove it anyway, anytime I have to prove something, I always start by doing f of negative x. So I'm going to do f of negative x just to see if it works out to be even. It's highly doubtful, but I'm going to check her out anyway. Why is it highly doubtful, you ask? Well, it's highly doubtful because our exponents are both odd. And when I take a negative number to an odd power, it stays negative. So here I did my substitution. What is negative x all cubed? True, it's negative x cubed. Ooh, that's a big bad x there. Then negative 5 times a negative x is a positive 5x. So is that the same as the original? No. Well, that means it's not even. So now what I've got to do is find out what is the opposite of the function. So what I'm going to do is I'm going to do the opposite of f of x, which means I'm going to take negative times that whole function, which is x cubed minus 5x, and I'm going to distribute that. Negative times x cubed, negative x cubed. Negative times a negative 5x is a positive 5x. And what do we see? Well, we see that f of negative x equals negative f of x. So what does that tell me? No, it doesn't tell me they're even. It tells me they're odd. It tells me that f of x is odd. Like so many of you. Most importantly, me. Okay? Now that kind of looks more like f of x. Alright, so there's your closure. Give her a go. Check your answers with your neighbor. See what you all come up with. Turn this in. Thanks.